Thanks very much, and yeah, I just want to thank the organizers. Really, it's a privilege to be here and tell you about our work and to be able to reflect on the past 100 years of quantum mechanics and also reflect on the next 100 years or even a few hundred years, depending how ambitious we are. And yeah, at this special time and place, both here on Helgoland and then in this year of quantum, it's really an exciting time. And hopefully I can tell you about some of the things I think are very exciting about using the tools we're now developing, in particular some of the systems, as Marcus Aspelmeyer was talking about yesterday, to control larger and larger objects and measure them in the quantum regime. And in our case, we're quite interested in using these as sensors for understanding some of the major questions we still have in fundamental physics. So before I get there, let me just show you this beautiful picture of our neighboring galaxy Andromeda. I mean, and it's really here on the 100th anniversary of thinking through quantum mechanics. It's amazing to think how well we can understand everything we see in this picture, at least what we see. The stars, the spectral lines, all the transitions, the atoms that make up what we see in this picture, we really have a huge, impressive degree of understanding of. And this was emphasized by Doug in the very first talk, as well as Jem in the last talk. But, and there's always a but, of course, when we look out into the universe, even if here in the lab on the Earth we understand things extremely well, when we look into the universe, we understand less and less. And as probably people well know, especially if you look in the outskirts of Andromeda or any galaxy, you see that the neutral gas is going much faster than you'd expect from the stuff you see. Even among the particles for sure we know are here, actually the most numerous matter particle here, possibly other than dark matter, are neutrinos. You don't see those at all in this image. And there's big open questions. Even if we have the framework of quantum mechanics, we think we understand the basic ways some things interact, outside of gravity, as we've heard quite a bit about. The particle content of the universe, actually, most of the stuff in the universe we appear not to understand. And so I've called this talk Quantum Sensors for the Invisible Universe because really, there's lots of invisible things we don't understand. We heard some really beautiful work and talk from Marcus Aspelmeyer yesterday about gravity, so I'm not going to talk about that. But maybe I'll focus on these easier challenges, let's say, related to what's in the universe, more so than what the fundamental interactions are. And as I said, really, in some ways, the most numerous things we know of in the universe, we don't have a complete understanding of. So I'll talk about neutrinos. We know that neutrinos have small but non-zero masses. We don't understand the origin of those masses. We don't understand why we haven't seen the right-handed neutrino states we think should exist. And maybe there's some sneaky neutrinos hiding back there that help us answer that question. We think in order to understand not just Andromeda or neighboring galaxies, but the structure we see in the universe, why we're here at all, why there's any galaxies and structure based on what we see in the cosmic microwave background, we need something that's not within the particle content we know that could have fallen in and formed the gravitational wells that this cosmological structure fell into. Of course, as a particle physicist, you really want to know what that stuff is, just not that it's there out there in astrophysically, and there's a major goal in fundamental physics to try to detect dark matter directly in the lab. And we heard some, actually in this conference already, a couple proposals for extremely challenging to detect dark matter candidates, but maybe ones we could think about. And then, of course, it's very important also to understand gravity, but we've heard a lot about that already this week. So the unifying theme of this talk is that the reason we don't understand these things, including gravity, is not because they're not important, but because these things interact extremely weakly with us. And in fact, we may need sensors that are as sensitive as our best quantum systems to see the tiny interactions they have. But even if we have, even if we could see these things interacting with a single atom or ion in a trap, we just don't have enough stuff. The cross sections are too low. And so quantum measurement and control of much larger masses than we've been able we're starting to build after 100 years of quantum mechanics through the really impressive work to isolate these systems that we've heard about, may allow us to start to untangle some of these pictures. And again, we've heard from Marcus Aspelmeyer and Marcus Arndt yesterday about really inspiring work in this direction, and we'll hear actually in the next talk, as well as later this session from Cindy and Yuen and Nergis tomorrow about similar macroscopic systems where we're really exercising quantum measurement and control. And this is a huge area now, I would say, in particle physics more generally, so I'm not going to talk I'm only going to touch on a bare fraction of the applications, and there's this nice Nature review article recently outlining where the community's going. So we've heard, in Marcus's talk yesterday that really, we've revolutionized in the past, recent decades how we measure tiny forces. This was pioneered by the same sorts of very hard sensing problems that I'm thinking about here. Could we detect gravitational waves? And before it was optomechanics, the gravitational wave community, and many of the experts here were thinking about what's measurable, even impossible, with sufficiently massive systems to see these tiny interactions. But maybe the exciting thing is now there's a huge range of systems that are over a huge range of masses, from the single atoms and ions at the zeptogram scale to the kilogram scale masses in gravitational wave detectors, but then everywhere in between. This is a nice plot from Marcus Aspelmeyer and Florian, one of the conference organizers, from only 10 years ago. But in fact, we've gone way beyond this now, and especially in the past 10 years, there's been a lot of work on levitated objects that we've heard about already in this conference, which maybe live in this femtogram to milligram mass range. And as we isolate these things better and better, maybe by levitating them, we become able to exercise more and more control and get larger and larger particles into these quantum regimes. And I think what I'll focus on is that for some mass range here, for masses below about a nanogram, we can actually see forces imparted by single subatomic particles of relevance to nuclear and particle physics. So in our lab, we focus on optical trapping of nano to micro-sized dielectric masses. So I think it's kind of amazing that just by focusing a laser, you can trap particles from kind of femtogram scale and mass. Those are 100 nanometer diameter objects up to tens of microns, just by maybe changing a little bit how we orient the laser. By trapping these in ultra-high vacuum, we can extremely well isolate them, so we can start to put these things, get low enough decoherence and interaction with the environment, that if we collect all the information, as we heard about from the photon fields, which are interacting with these particles, we can really measure and see forces interacting at these at the limits, or where quantum mechanics really dictates what we can do. Putting numbers to that means for maybe our smaller particles with femtograms of masses or 100 nanometer diameters, we're reaching force sensitivities around maybe 10 to the minus 21 newtons per root hertz. But more important for this talk is all the things I'm talking about don't just require excellent force sensitivity, but they require good force sensitivity for a given amount of mass. You need enough mass for the neutrino to interact or the dark matter particle to hit it. So the real figure of merit is acceleration sensitivity, and this is what really pushes us to these larger masses. We also heard about it from Marcus when talking about gravity. If you want to do quantum physics for some of these very weakly interacting things, you need to go to heavier, or you improve by going to heavier and heavier particles. So before I tell you about our work, let me just show the people who are really doing it. We're a particle physics experiment, so we have to have an acronym, but really it's just a small team of people working on a couple optical tables at Yale. So for our large spheres, and large here again is maybe 10 microns sort of diameters or nanograms of masses, but starting to get the control that we can talk about these things in the quantum regime. I'll give you a little flavor of the types of things we can do and the control we have over the particles. Of course, the first thing you need to do is get these into the trap. For large particles, we can do this kind of thing where we put it on a glass surface. It's really a dust particle, though. The van der Waals forces are very strong, so you have to shake it very hard. It's something like 10 to the 6 G to even get it to come off the surface. But we can do that with a piezo stack, and if we put a laser there, actually we can lift it up, and here you see a single particle being trapped over and over. When it's in focus, it's actually sitting on that glass, and then you see it pop up, and then we can set it back down and pick it up again in some little amount of gas to keep enough damping that the trap's stable. So if we have a good particle we like, we can put it in a trap. The next thing, though, is we want to get to high vacuum, so we can have very low interaction with the environment, very low decoherence. But it turns out when you pull a glass particle off of glass, you get triboelectric charging, just rabbit fur on glass sort of charging. And these particles always come off with maybe thousands of extra electrons on them. But Marcus also alluded to this. You can do kind of a sophisticated modern version of the milk and oil drop experiment. We apply an electric field pushing on the charge on the particle and just measure its motion in response to that electric field. So this is just a plot of that motion, though calibrated into units of the net charge of the particle. And we see it moving, and then we start shining UV light on it, and we see its motion decrease. In fact, in this case, we go too far. So we're knocking electrons off, and now we have more protons than electrons on this ball with about 10 to the 14 of each. But that's okay, because we can start knocking electrons back onto the particle from the gold surface nearby. And here at the end, you see that we can add one electron at a time. And with very high signal to noise in a small electric field, we can see a single electron added to the particle. And when we get to 0 here in these units, we have exactly the same number of electrons and protons on this ball, which has about 10 to the 14 of each. So this is has a monopole charge of exactly 0. The next thing we need to do, though, is actually spin these particles. It turns out they're slightly elliptical, and they also have asymmetries in this charge distribution. Even if you have exactly the same number of electrons and protons, those aren't distributed in perfectly spherically symmetric nature. So we use circularly polarized light to actually transfer a little bit of angular momentum from our trapping beam to the particle. And actually, because the damping is so low in high vacuum, even for amorphous silica, something you wouldn't expect necessarily to interact with the angular momentum of the light, you'll see it spin up faster and faster to a terminal velocity over the timescale of a day. And this is actually in megahertz here, so this few micron particle is spinning up to a terminal velocity around 5 million rotations per second. So actually the fastest you can spin a solid object of this size, and if you go much faster, it's going to explode from centrifugal stress. So that's just a limit of materials. If you go to smaller particles, you can get to gigahertz rotations, and these are the fastest human-made rotors we've made. But this is important because it gyroscopically stabilizes the particle so that its angular orientation is fixed and we don't get confused by it kind of processing around and interfering with our measurements at the center of mass. But it also averages away any higher order multipole moments except for the dipole moment of the charge distribution along the spin axis and allows us to control even further beyond having exactly the same number of electrons and protons, be able to control the electric state of the particle. This is crucial, of course, for force sensing. Then, if we want, we have this, perfectly neutral particle spinning a million times or a few million times a second in the center of our vacuum chamber. Now we can monitor the center of mass degree of freedom. This is a plot. You've seen maybe similar plots in Marcus's talk, but this is for much larger spheres, showing the motion of that particle here in meters per root hertz. So that's a nanometer in the center of the plot here as a function of frequency. These heavy oscillators are actually quite low frequency oscillators below 100 hertz here, but you see a relatively high Q mechanical oscillator ringing at its resonant frequency, and then we just watch it in real time, as Marcus described, use the photons interacting with it, measure the information carried by those photons about where the particle is, and apply an active feedback to slow it down. And when we cool this particle to be at the kind of noise level of our system, its center of mass degree of freedom is as still as though it were in thermal equilibrium with a 50 microkelvin gas. It turns out actually that the internal degrees of freedom, the phonons, are 1,000 Kelvin maybe even, but there's one special degree of freedom, the center of mass degree of freedom is extremely cold, and maybe another way to say it relevant for us is that it has extremely low interactions with the environment and can be a very good sensing degree of freedom. And then maybe finally, if we want to, I told you we still have a dipole moment oriented in the vertical direction, and if we want, we can apply torques on that dipole moment, kind of the analog of a pi pulse in NMR, and be able to rotate around that dipole moment and symmetrize the charge distribution even more. So this is, I know, a lot of stuff, and maybe folks are in a variety of fields here, but the point here is that this is all enabling technology to have the control to be able to do very sensitive force measurements with these kinds of objects in vacuum. And if you look at the dates here, really this is all stuff from the past maybe 5 to 10 years. So as Marcus Espelmar pointed out, Ashkin was first trapping these things in the 70s and 80s, but then it took many decades, and within the last decade there's really been a resurgence of interest and I think huge progress in this field. Okay, and one more thing before I get to the actual applications is that, of course, once you have one, you want lots. We heard about this also in beautiful work from Misha Lukin in the community building, tweezer arrays for Rydberg atoms. Of course, we also want tweezer arrays for these sorts of nano and microparticles. For neutrinos, dark matter, I told you want lots of stuff. Maybe there's some limit to how big you can make each particle, and then you want lots of them. So this is not yet anywhere close to what folks are doing with neutral atoms at this point, but this is an array of about 50 of these made with very similar techniques, and these are individually controllable tweezers, so I'm obligated to make the Yale logo with, this is work by Ben, to make the Yale logo with microspheres. And I should say this is a little bit of a joke, but even though this is only 25 spheres, there's thousands of atoms in Rydberg tweezers, but this is 10 to the 15 atoms, and that's really, that's crucial for being able to see things that want to interact very weakly with our particles, and of course why you can't maybe do the same physics targets we're looking at with single atoms and ions. Okay, so what do we want to do? So what I'll tell you about in this talk is that we really want to be able to detect the forces imparted on these really large, by maybe quantum standards, objects from single subatomic particles. And I introduced the two I'll focus on here already, neutrinos and dark matter. So imagine we were to take radioactive nuclei and stuff them into this micron scale sphere. Our favorite sort of radioactive nucleus as a detail to do would be something called an electron capture decay. It was something that wanted to emit a positron but couldn't, so it captured an electron, and basically it emits a neutrino and nothing else with very high momentum. So the neutrino comes out of the sphere. Of course, the nucleus recoils, but it doesn't go very far. It stops within the sphere. It rattles around and makes all kinds of messy phonons and everything else. But by momentum conservation, the whole sphere has to recoil with equal and opposite momentum to the neutrino. Now, of course, neutrinos, we have no chance of detecting individual neutrinos directly. This neutrino has a mean free path over a light year in lead, so that thing just flies out into space, and we could never, when we build neutrino detectors, we build kiloton detectors and put them next to a reactor or something shooting out, 10 to the 14 neutrinos per second, and then maybe we get a few. So we would just have no chance of detecting this neutrino itself, but if we could see these really tiny kicks as the neutrinos fly out, actually we can event by event learn something about the momentum carried by those neutrinos. Of course, the other thing, and actually there's been a couple mentions of this already in this conference, we could do is instead of putting things in that are leaving the particles, we could look for some particle to fly by and interact with the sphere. So imagine you have a dark matter particle flying by. Really the minimal interaction we know for sure that dark matter particle should have with stuff in the lab is gravitational. And you could imagine if this is a Planck mass black hole, like we've heard from both Carlo and Marios earlier about in the talk, this would give a little tug on the particle and maybe give it a pull. It's interesting actually to ask, could we see that even in practice, in principle? And the answer is, well, yeah, maybe, but you're really going to have to know quantum measurements well, because the hardest thing about doing this for Planck mass black holes would be beating the standard quantum limit, or continually measuring the position and momentum of this particle. You'd have to beat it by something like 30 dB invariance. So that's a very hard thing, but maybe not quite as hard as some of the things we've heard about when talking about gravity. But in the shorter term, gravity is an incredibly weak interaction. If dark matter has stronger but gravity-like interactions with normal matter, maybe we could see them this way. And these are really completely different ways to see dark matter than all the detectors that have been built. So the basic idea in either of these is the sphere's just sitting there and all of a sudden it gets a kick. So if you imagine this is some quantum harmonic oscillator sitting in its 3D potential, it has some average energy. Marcus told us that you can actually measure the position in a weak continuous measurement, the position of this oscillator in phase space, and use that information to feed back in an optimal way and cool it to the ground state. Same idea here, except instead of cooling, you can cool if you want, but you don't really need to. If you're doing a good enough measurement that you could have cooled it to the ground state, it means that you could see a change in the momentum of the particle by something like the ground state uncertainty. So this gives you a standard quantum limit, or SQL, on the smallest momentum you can resolve for this kind of weak continuous measurement. That's something like the square root of the mass times the resonant frequency of the trap. This was maybe derived by our session chair and others, other luminaries in this room. But that's really, actually exciting for us, because when you plug numbers in here, you get these numbers that are like, 10 to the minus 24 Newton seconds, are really tiny numbers. But when you convert these to particle physics units, these are really, very relevant scales. So if I had this 1 MeV momentum neutrino leaving here, and I have a 10 keV momentum resolution, you can actually measure this neutrino with signal to noise of maybe 100 when it comes out. So that's the plan. Let me tell you in the second part of the talk about first some proof of principle measurements and then where we're going. So just to show this isn't all kind of crazy, and we can actually already start to do some of this stuff, our student Xiaosheng has actually been able to show you can detect single nuclear alpha decays in our micron-sized spheres. Now these carry a lot more momentum than neutrinos. So I just said a neutrino might have 100 keV to an MeV of momentum. So we start with alphas because they have 100 times more momentum. So as far as subatomic particles go, these are really, this is like a cannonball coming out of the sphere. But we can do this with much larger spheres, which for various reasons makes it technically easier for us to start with. Turns out really the sensitivity is not so much the problem in these experiments, but we need to get radioactivity into these like dust-sized particles, and we don't want to inhale radioactive dust. And just like Marcus Arndt was telling us, it's a challenge to load some of the very interesting biomolecules and things like that. The loading of radioactive particles has been one of the technical hurdles to realizing this. But Xiaosheng was able to do this in maybe a slightly complicated way, but that worked well for the first demonstration, which is actually we take radon gas. This is not the radon in this room, but the radon from the thorium chain, in part because it has a short half-life. It decays to a polonium ion, it turns out, which we can drift onto the particle surface. That further decays, and half the time the alpha will go out, and the lead-212 daughter will get implanted into the sphere. So if you're following this decay chain along, we're down here at lead-212. If you have really good eyes, you might see that as a 10-hour half-life, and that's the longest half-life in the chain, but it's still radioactive. So over the next tens of hours, those lead-212 atoms we get in are going to decay. There's bismuth-212 and polonium-212 that can both decay by emitting alpha particles. But then after several times 10 hours, all the radioactivity is gone. We can open the chamber, breathe in the dust particles, and not have to worry about radioactivity at that point. So Xiaosheng was able to actually demonstrate this works and get lead-212 radioisotopes into our spheres. These are implanted within the surface at depths up to about 100 nanometers. And the way we know for sure they're there is actually just this thing I told you about doing this Millikan oil drop style experiment with the charge, where we know exactly how many electrons and protons we have on the ball at some time. And then if one of these radioactive decays occurs, all of a sudden some charged particle zips out. And we can just see that without any question. If we're monitoring the net charge of the particle by applying a weak electric field at some frequency, we can see how much it's moving in that field. Again, this is that net charge measured with that Millikan oil drop style experiment over now tens of hours. I told you the relevant half-life here is about 10.6 hours. So this is a few days of data. And actually here, what you're seeing is every time this line shoots up, that's one lead-212 nucleus or one of its daughters decaying in the sphere. And these are just very obvious. Maybe if you zoom in on the inset here, you can see the charge versus time, and every little step here is a single alpha or beta decay. So we can actually see single nuclear decays happening in this object that might only happen once every hour or once every tens of minutes with essentially zero background. So all the natural radioactivity, unless it's in the sphere, we just don't see it at all. So we can count individual nuclear decays and really be sure about them. One interesting thing here is actually, you might expect that the alpha decays carry 2 protons out of the particle. It turns out, though, that those alphas always knock lots of electrons out of the surface on their way out. And some of these steps are extremely large. Actually, we see single alphas that knock maybe 10, 50, 100 electrons on the way out. And if we don't load our spheres with radioactivity, we can see a single sphere sit there in the chamber for days without seeing any charge changes. So this is a very good background-free way to see that something occurred in the particle. But of course, what we're interested in is not just seeing that a decay occurred, but measuring the kind of kinematics and reconstructing the kinematics of that decay. And so if we zoom in now, instead of a few days, zoom in maybe on a minute time scale around one of those charge changes. So this is the same sort of data that was on the previous plot, showing the charge versus time, where initially the particle started with 7 extra electrons, 7 more electrons than protons, and then all of a sudden it has 13 extra protons. And you can just see very clearly when that happens. The exciting thing is that if you look at the X, Y, and Z motion, the motion in 3D and the other coordinate degrees of freedom, exactly correlated with when that charge changes, we see a kick here. This is already calibrated into the response we expect for a momentum kick to the particle, but we see a momentum transferred to the center of mass of the particle that's expected with a pretty high signal to noise here for this alpha decay in this large particle. And if we zoom in further here now to a few hundred milliseconds, half a second or so, again, you see this charge change, and exactly coincident with the charge change, the yellow here is now our reconstruction of the center of mass position of that particle. So it's a 3-micron diameter particle. Initially, its center of mass degree of freedom is still to a few nanometers, and then just with your eye, you can see that the center of mass moves by 20 nanometers right at the same time that alpha particle zips out. And when we calibrate that and reconstruct it, it's exactly the momentum we expect. So to our knowledge, this is the first time you've been able to see the force imparted by a single subatomic particle on a much heavier mechanical sensor. So the sensor is trillions and trillions of times heavier than the alpha particle that's coming out. But with the level of measurement precision we have, just by measuring the photon scattering from this object and optimally measuring that information, we're actually able to see these kinds of very tiny forces. Okay, so this is alpha particles. As I told you, that's a big momentum transfer by fundamental particle standards. But where do we want to go? I mean, for alphas, you can detect them with conventional detectors, but really we want to go to neutrinos where there's no hope of detecting the particle leaving, and you really want to see only this recoil. And all we need to do actually is just scale these things down to smaller sizes, so 100 nanometer, 150 nanometer diameters, the same sort of size scale that Marcus was telling us yesterday have now been really cooled to the quantum ground state and controlled in the quantum regime. And we've also in our lab, this is work by our grad student Yuhan and postdoc Tom, been able to do sensing now with these smaller femtogram mass particles. So this is just a plot of the measured noise, power spectral density or amplitude spectral density versus frequency for one of these smaller particles. These smaller particles we can trap and confine more tightly, so this is now 50 kilohertz resonant frequency. And when we measure it in force units, of course, it's in SI units in very tiny, 10 to the minus 20 sort of newtons per hertz units. But our measured noise here in blue, maybe the thing to point out for this conference, is really now pretty much dominated, especially on resonance, by the back action of the measurement itself. So the same photons, in this case we're using both to trap and image where the particle is. The quantum mechanical fluctuations and constraints on measuring where the particle is that come from that back action are the dominant noise source in our measurement. And if you integrate this blue curve here and estimate what the momentum sensitivity we should infer from it is, you get about 65 keV. And you can compare that to maybe the ideal case for the standard quantum limit of about 24 keV. So we're really now reaching, even though we have a little too much back action and we'd like to lower that further, we're starting to get into this quantum measurement regime where we can do the sorts of neutrino physics we want. And again, I told you that it's easy to, if we can get the right isotopes in the spheres, get neutrinos zipping out of here with a few MeV of momentum. And this is not a neutrino leaving, but this is just to really prove that. This is the calibration we do where we put a single electron on the sphere and then hit it with an electric field pulse that mimics the same momentum we might expect from a neutrino in that radon decay chain I just showed you. And this is one of those 5 femtogram particles. It's ringing, and then all of a sudden we kick it, it's ringing more. Just by eye, you can see that, and that's actually exactly the sort of signature we'd expect from a neutrino leaving. So the point here is that we could see neutrinos if we could get those same radioisotopes into these smaller spheres that we've recently demonstrated we can get into the big spheres. There's some technical challenges doing that, again, mostly related to the health and safety of radioactive nanoparticles, but once we're able to load those particles successfully, we'll be able to start doing really neutrino physics on the tabletop, not in these large, many kiloton experiments sitting in a nuclear reactor, but maybe learning something we couldn't have learned about before about neutrinos just in an optical table in our lab. Okay, so that's the near-term future, but let me just, in the spirit of this conference, maybe even thinking in the next 100 years of what we could imagine, where could this go? I said already, actually, the sensitivity, I think, at the kind of standard quantum limit, or at, just starting to breach into relevant constraints from quantum mechanics is really super interesting, and we can do, actually very relevant searches for example, heavy right-handed neutrinos. We've only seen left-handed neutrino states interacting. We've never seen the right-handed states we think should be there. Maybe we can see them as the wrong momentum coming out of these sorts of decays. We can search for dark matter, maybe these little Planck mass black holes, if they couple through a force that's stronger than gravity in addition to gravity, at least at short distances. We could search for that. But really, the ultimate potential, I think, of this stuff lies in the future. We're just really, as I said, in the first decade of starting to really push these systems, and there's a huge amount of potential we heard about from Marcus for testing gravity, but I think also searching for these invisible particles. And I put one up here. This is a very simplified view, but imagine this neutrino that actually comes out of the sphere is not it's very much like what we heard about from Magdalena yesterday. It's actually a superposition. The electron neutrino is not a kind of real propagating neutrino. It's a superposition of three neutrinos that we uninventively call M1, M2, M3, which are all mixed together. And really one of the holy grails of neutrino physics would be able to projectively measure, collapse this state and measure the masses of those neutrinos and also the mixing probabilities between those mass states. The world is spending many billions of dollars to measure these mixing elements as we speak, and if we could, do this on the tabletop, that would be super exciting. This does require going beyond the standard quantum limit for sure, but if we're able to mechanically squeeze these objects and learn only about these momentum kicks, push the noise into the position quadrature, maybe doing this sort of thing is possible. And the same sort of ideas maybe would allow us someday in the coming 100 years, I hope for sure, to start searching maybe through dark matter, through its gravitational interactions alone, at least for sufficiently heavy dark matter up around the Planck mass that actually looks plausible. So very similar to some of the candidates we heard about. And then in parallel, we're really in the early stages of this community, and we want to extend these to new materials beyond the kind of glass spheres we've been talking about, and we're actually working now to start trapping solid xenon particles, radioisotopes of xenon, as well as eventually maybe tritium for really fancy sources of neutrinos coming out of these. So there's, this is a really general, I hope, technique that just relies on what we can measure and with these kinds of systems, and hopefully can really extend it to the future. So I see I'm out of time, so let me just stop there and I'll leave my summary up here. Thanks very much.
Thanks for a nice talk. We have time for questions for Dave.
Thanks for the talk, David. When do you think you might be able to detect neutrinos with this experiment?
So to detect a neutrino coming out, we know as soon as we can get radioisotopes safely, and we can. So really, we think that's like a few months, hopefully, timescale. I'm endlessly optimistic, but I don't think it's more than a year. And then, there's a program of really trying to measure those in great detail to actually detect the differences in the momentum of the neutrinos from the different mass eigenstates is a longer-term goal, but who knows in the coming decades, yeah.
Is there anything that you can do on the spin side? Like you're also controlling the spin of this object, and the neutrinos and all the particles that are emitted also have spin properties that are well defined. Would that help in any way, or could you detect it?
Yeah, so it depends so for kind of angular momentum, yes. I mean, we could in principle control the angular degrees of freedom, and groups are now cooling the rotational degrees of freedom of these objects also into quantum measurement regimes. And of course, as these particles come out, they have linear momentum, but they're at some radius from the center of the sphere, so they impart both linear momentum and angular momentum. As far as spin things, yeah, I mean, there might be some chance to use spin polarized masses. Xenon 129 is hyperpolarizable, so maybe we could have a hyperpolarized ball of nuclear spins in some of these, and that's interesting for lots of models, dark matter models and things that couple to spin.
Thanks for fascinating outlook on these possibilities. I wonder if there is any optimization of the mass of these nanoparticles. It would seem naively that the lighter the better for the recoil, but maybe the way you can quantum control the ground state set some optimum. So yeah, what would be the ideal mass for the neutrino aspects of these things?
Yeah, it's a really excellent question. As you say, in principle, to get smaller thresholds, you want to make the mass smaller. The problem is that the radioisotopes we're putting in have finite half-lives, and we're trying to see very rare processes, like maybe 1 in 10 to the 10 neutrinos goes to a heavy state. And so there's just like, if you have something with a half-life of a year, you need a certain number of atoms to be able to ever have a chance of seeing that. And so we basically want the largest particle we can that can see the momentum transfers. And then we want arrays of them once we get one. Yeah.
Questions for Dave? I could ask a question. So you discussed, or you showed this plot of maybe using squeezing, mechanical squeezing.
Yeah. Yeah, this, cartoon, I would say, yeah.
Neutrino mass measurement. How much squeezing would you need for this particular application?
Yeah, so for this application, it's about 20 dB invariance in the momentum, and I was going quickly, so I should just say these are really nice results that were also in a poster from Andrei Militaru and Lucas Novotny's group showing 7 dB of squeezing already of the mechanical motion in the momentum quadrature. So, you know, the field is just starting to get started on this. Marcus's group, you know, there's really a huge amount of work. It's not obvious how much squeezing we can get, but 20 dB, I would say, is a lot less than what they're thinking about for, you know, equivalent for the gravitational measurements.
Any other questions? If not, let's thank Dave again.